Good evening and welcome everyone to ProLighting webinar series. My name is Minoj, Director of ProLighting Group and Program Manager of workshops and our webinars. We have conducted several workshops in past years for lighting technologies. Some of you might have already participated for those workshops with us. As a part of our community service, we have decided to conduct a series of webinars that will cover technical and practical topics in construction sector. I am very proud to convey you that our speakers well experienced and leading professionals in the field with their academic and industrial experience, some of them from foreign countries as well. We will cover hot topics in civil, MEP, it means mechanical, electrical, plumbing services, lighting, architectural, project management, contract management, quantity surveying, etc. Today, our topic is modern electrical installation. Today, our guest speaker is Dr. Asanka Rodrigo. Dr. Asanka Rodrigo is Senior Grade 1 Lecturer and Director, Postgraduate Studies, Faculty of Engineering, University of Moratuwa. He is the former Director General of Sri Lanka Sustainable Energy Authority and also, as you know, he's one of leading electrical consultant in the industry. And now I am going to hand over webinar platform to Dr. Asanka. After the webinar, you can ask your question. Doctor will answer accordingly. Good evening, Doctor.
Good evening, Minaj. Let me share my presentation first. I hope the presentations are visible to you and it's audible. Is it visible to everyone from the attendees? Can you please confirm whether it is audible? Yes, okay. Thank you very much for that confirmation. So first of all, I would like to thank the ProLight Group and especially Minaj for inviting me to deliver this the lecture. And today the topic is, as Minaj explained, the modern electrical installation. So that I wanted to give some kind of because I'm doing similar kind of lecture for even IET, ISL, and many other places. Just to educate the people, because I hope all of you are practicing in industry so that you have to update every day. So because this the electrical installation field is the changing rapidly with the modern technology, so that it's always good to the update you by yourself, so that and also because of that I thought to share some of my knowledge with you, so that will be benefited to the industry, so that ultimately our main objective is to have a good industry, so that where everyone will practice in good engineering practices. So that is the ultimate goal. So that with that note, so as because the ProLight Group asked me to deliver a lecture on this modern electrical installation, what are the things and what type of factors we have to consider, especially working with modern electrical installation. So if I move, so now when you look at this electrical, I'm mainly targeting on the electrical systems which are used in the modern building. So that when you look at the electrical systems in building, of course we know that the main thing is we have to build and create the better and the consistent productive environment where the people can live with and work with. So that because of that, to achieve that one, we need to have a better lighting system, of course, because we are our biological cycle is the tune with natural lighting, so that of course we need to have a when we are replacing the natural lighting with the artificial lighting, we need to have a better lighting system. And there are a lot of the practitioners where we have to look at those type of human-centric lights in the modern building, and also the comfortable space and temperature, humidity, because of course we all experiencing that okay the temperature in the outside environment is increasing, and because of that we want to create the suitable and the comfortable environmental condition and the humidity, air quality, those type of things within the building. And also the other thing is the convenient power and the communication ability. So that is also one of the key factor in the electrical installations. Ultimately, whatever you do, finally we need to have the reliable system as well as the protection for human beings and all the livestock, as well as the property, because you may have heard that in the recent past there were a lot of the building collapse and the fire in the building environment. So that because of that the people are putting more and more concern on the protection as well as the reliable supply. So that I'm mainly focusing on, so with the new rules and regulations, because of those things, because these are evolving, and with the practice, and people get to know different type of things, so that they update the different the requirement in these type of the places, including the modern the building. So that we have to, that's why these are changing day by day, so that with the others experience we have to modernize, and we have to update our knowledge, and we have to practice the good practices, so that we can ultimately come up with the good electrical system in the building environment. So that's the main point, so that I'm mainly focusing on. So in order to give a reliable supply and the protection for the lives and the property, so what type of things we have to have, and what are the new the current trends, and what are the new regulatory changes, and the other practices where that can help to achieve that reliable and the protection for the human beings, and the reliable part of the system, as well as to give the protection for the lives and the property. So that I'm mainly focusing on that part because I have given only 1 hour time period, so that within that time period I cannot cover obviously the many things, but I'll mainly focusing on that aspect. So in electrical installations. Now, when you look at this electrical installation, we know that we are practicing IET wiring regulation, or the BS 7671 in Sri Lanka. So that when you look at this IET wiring regulation, I'll first give some of the background about this IET wiring regulation, or the BS 7671. So that was started in way back in 1882. So as a rule and regulation for preventing fire risk arising from the electric lighting. So that was the initially this standard was started like that in way back in 1882. So even though now we are calling it as a IET wiring regulation, so initially that was started like that. And from time to time, so this is the first edition of this regulation. And then time to time, there were many changes with the modernizing of the requirement, modernizing of the things and the requirement. So then when you look at the third edition, which was published in 1897, so that the name was changed as a general rules and recommendation for wiring for the supply of electric energy. Now you can see earlier that was started with something like the preventing fire related to the electric lighting, but now it has been changed to the general rules and recommendation for the wiring. So that that's how the third edition came in. Then from time to time that was changed, and when it comes to fifth edition, so I'm not taking all the in a chronological order, but when you look at the the fifth edition, so rather than giving a very long the title, so they changed this regulation as a wiring rules in 1907. And then the later, so when you go to something like the 80th edition in 1924, that was changed as a regulation for electrical equipment of building. I can see that now it's more moving towards the building and the building related wiring, so that like that. And when you look at then there were several changes, and in 1966, that was a very turning point. That's why I have highlighted that in the 15th edition, where that was changed as a regulation for electrical installation. So in 1966, so this is the time where even in Sri Lanka, we started to adopt this the regulation, so that even IESL promoted this regulation as a wiring regulation, and they did the different type of CPDs, and that was the time where even the IET wiring regulation was popularized even in Sri Lanka. At that time, it was IEEE wiring regulation, where then later it was changed as IET. And then that was the 15th edition. Then there was a 16th edition, which was published in 1991 with the red color cover. And there were several amendments from time to time, and they publish those the revisions in different years with different colors, like green color, yellow color, like that. So that these are the older ones. And then in 2004, so this was published as the brown color. You can see it here. That but all of them were named as 16th edition. Then in the 2008, the IET published the 17th edition. In the 17th edition was in red color. So in 2008, and but when you look at this one, because there is a time where so this modernization of the building happened, and the lot of the modern techniques were adapted in the building environment, so that because of that, they wanted to change it very frequently. So that even though that was published in 2008, so there was a first amendment in a green color, the cover. So as that was mentioned as amendment number 1 of 2008 version. And then again, there was another amendment in 2013. And then again, another amendment in 2015. Likewise, there were several amendments in time to time, because the IET group got to know that, okay, because they have to do certain changes from time to time. And because these the requirements are changing, we are adapting more and more the new equipment, the power electronic based equipment, and there are a lot of the new issues are coming in, and because of that, they wanted to tighten the rules and regulations, and they have to some of the rules and regulations they wanted to the remove and the ban. Likewise, there were a lot of changes that happened from time to time, and the third amendment was done in 2015. Then they realized that rather than going for these amendments, it's better to release a new version. And in 2018, they released the new version as the blue color edition. So as the 18th edition. So that's what we are currently practicing, and that is the latest edition. So that there will be a new edition very in recent past. So the very recently, and but at the moment, the current edition, what we are practicing is the 2018, this 18th edition one. Now, so this is IET wiring regulation, or what we call as a BS 7671, or the wiring regulation. But the one can argue that, or one can ask that, okay, why this BS 7671 for Sri Lanka? Is there any requirement? So, why do you want to follow the IET wiring regulation in Sri Lanka? Because that is the UK based one, and the European the standard. Why do you want to have it in Sri Lanka? Is there any requirement, or do we want to follow IET wiring regulation in Sri Lanka. So if I ask the same question, so what is your answer? Do we want to follow this one, or is it by tradition we are following this one? Of course, as I said, when you look at this, we are by tradition also we are following this one from 1966, so even before that, we were following this one. But it is not only the tradition now, because when you look at this regulation, so the regulation is now the legalized in Sri Lanka, because as you know that in 2009, so we published the Electricity Act in Sri Lanka. So that in this Electricity Act number 20 of 2009, basically regulated all the electrical activity in Sri Lanka, including the power generation, power transmission, distribution, as well as the utilization. Utilization is use of the electricity in building and any other end user, the places. So that when you look at this Electricity Act, there is a amendment for that Electricity Act in 2013 as well. But as per the act is the legal document, so that it's passed by the parliament, and because of that it's a law of the country. So these acts are, because we have the constitution, and after the constitution we have different acts for different type of sectors, areas like that, and act is a legal document. And act based on the act we can publish rules and regulations. So that even for this the Electricity Act, so in 2016 the Power Ministry published the regulation, so that called Electricity Regulation 2016, and in this one that calls as the Electricity Safety, Quality and Continuity Standard. So that in 2016 standard or the regulation was published, mentioning that it's the big regulation, but I'll just extracting what is related to this one. So now in this regulation, not the act does not say anything about the what type of standard we have to follow, but it's given in the regulation, 2016 regulation. Regulation is under the act, so that because of that, now as per this regulation, it says that so the Sri Lankan standard requirement is so blah 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 like that. We have to follow at that time. That is the 17th edition. Oh, but you can see it says the 17th edition. Oh, latest. So that then obviously that's a legal requirement. Now in Sri Lanka with this Electricity Act, this IET wiring regulation has become a legal requirement where you cannot deviate. So no matter whoever the consultant, whoever the contractor, so that we have to follow the IET wiring regulation in Sri Lanka, or what we call as a BS 7671 in Sri Lanka. If you are doing any electrical installation, so then this is the standard, or this is the regulation we have to follow. So that it's a legal requirement. If someone deviate or if someone violate this regulation, then anybody can take him to even for a court, and you can put even the file a case against you, because it's a legal requirement. Now, not like the previously. So now this following IET wiring regulation, whatever the latest. So if the whatever latest one is a legal requirement in Sri Lanka. So that's the background of why we want to follow this IET wiring regulation in Sri Lanka. Now, when you look at this one, it's not like a Bible where you cannot can apply for anything. So that when you look at this IET wiring regulation, normally the voltage levels are categorized as per the IEC. So that those are categorized as extra low voltage, and the high voltage. So when you look at this IET wiring regulation, that is applicable only for the low voltage and the extra low voltage, that is a voltage below 1000 volts AC or 1500 volts DC, and whatever the high voltage, there are different codes and practices. So even in Sri Lanka, so for example, when normally high voltages are handled by the supply authority, so that they have their own standard and the regulation. That is not a part where I'm going to touch. So that, because when you look at these different type of voltage, obviously we know that extra low voltage where you have a very minimum risk of electric shock, but when you go to low voltage, there is a the risk of electric shock. When you go to if you are handling with the high voltages, then obviously, so not only electric shock, but there can be the risk of arcing and burn. So that's why we are the confined to a low voltage, so that this standard is confined to a low voltage application. There are certain other the places where we cannot apply this low voltage, even though they are low voltage. Some locations we cannot apply, that is also there. But I'm just telling that, okay, that this IET wiring regulation is applicable for whatever things we are doing in utilization side of the electricity, and the voltages are less than 1000 volts AC or 1500 volts DC. That is the first thing you have to keep in mind. And then when we go to this, the practice in this IET wiring regulation, in the regulation, so that's talk about different type of earthing arrangement, or basically in electrical installation, we can, any electrical installation, we can subdivide into two parts. One is the source side, other one is the installation side or our equipment side. So when you look at these two things, where we can earth the source or the source neutral point, or we have to have earth for the installation side. And depending on those the earthing arrangement, the IET wiring regulation basically discuss about the four different type of earthing arrangement: TT, TN, the TN arrangement. We have TN arrangement, you have TNC and TNS, as well as we can have, there is an option to have TNC part of the installation and TNS part of the other part of the installation as well, that we call as a TNCS. So the other one is the IT. So that altogether, when you look at in general, there are 5 different type of earthing arrangement. So the one is the TT, other one is TNC, TNS, and we can have a combination of TNC and TNS. Then the other one is the IT earthing arrangement. So the first question comes in when you go to modern installation, what type of earthing arrangement we can practice in Sri Lanka. So now when you look at like that, so if I ask from you, okay, what earthing arrangement you recommend when you are doing or when you are working with the building in Sri Lanka? So because I asked the same question in many the presentations, so the most of the people said that, okay, it's TT. And the most of the people thinks that, okay, Sri Lankan system is the TT, but it's wrong. Because if we are adapting, because there is now when you look at this IET wiring regulation, as per the regulation defines different type of earthing arrangement. So that if we now we have adapted the IET wiring regulation as it is in Sri Lanka, but there are certain countries where they adapted, but there are certain type of the deviations. So some of things they have not adapted as it is. Now, for example, when you go to Singapore also they adapted the IET wiring regulation, but they name it as their own standard. But when you look at that one, they specifically says that in Singapore they are not practicing TNC systems. So that you cannot have TNC system in the Singapore, but you can have any other. But like in Sri Lanka, when you look at Sri Lanka, we don't have such things. So that because of that, keep in mind, we can adopt any type of earthing arrangement in Sri Lanka legally. We can adapt anything. Even utility cannot say that, okay, you cannot go like to any other things other than TT. So that it's up to the designer. Designer can decide what type of earthing arrangement is needed for Sri Lanka. But there is a certain restriction. So that is only a restriction, because when you look at our distribution system, that is the normal distribution transformers, you may have seen that they are running, okay, they have only the 4 conductors, that is 3 lives and the neutral. And normal practice in the distribution system in Sri Lanka is we are not continuing the earth connection because that is mainly because of to reduce the cost, not any other things. Because in early days, because we were in a we are a poor country, and when the utilities are adapting this one to reduce the cost, so they have adapted this TT or the normal distribution arrangement where they have the transformer in one location where the transformer has a neutral rating separately, and they run only the phasors and the neutral conductor only. So that because of that, we don't have a earth conductor continuity from the source to the installation place. So because of that, if we are getting a supply from a normal distribution transformer or normal distribution system, so that is up to 42 kVA, then we can only adapt TT arrangement. But when we are going for a large installation, most of the large installation, our utility, CEB or LECO, they are providing their own transformer to cater the building or the cater to the installation. So if you have your own transformer, especially when you are going for a ST bulk or the LT bulk connection, then you don't have a restriction because it's your own transformer. So either you can design it as a TT system or TN system. Because what I am telling is now the most of the cases, you design even for those type of bigger installation, with the TT, ultimately you will face certain problem of earthing because in the TT means your source earth and the installation earths are separated, electrically separated. Sometimes in a restricted area, you will not be able to put those earth and keep electrically separated to earth electrodes. So that because of that, rather than facing that type of problems in electrical installations, always better to go with, by considering all these specs, better to select a most suitable type of earthing arrangement for a given installation. So the traditionally, rather than going with TT, because the TT is, my view is, it's not a very good the system in terms of the protection and safety, because you have the very high loop impedance. Higher the loop impedance, you will get a very low earthfall current, so that the earthfall coordination is very difficult in the TT system. In Sri Lanka, we adopted TT system merely to reduce the cost of earth conductor. There is no any other reason to go, because when you look at many developed countries, they have a distribution system, but they run a separate earth conductor from the source to the source point, so that they are running with the TN systems. But in Sri Lanka, we are running with the TT system only for distribution, the connections. But for the ST bulbs and the LT bulbs, you can easily go with the other type of earthing arrangement. That is one thing I want to highlight. And also, other thing is, when you look at this, the regulation discuss about the different type of earthing arrangement and the earth connections as well. Because now you have to keep in mind, in the modern building, what they are talking is the equipotential bonding. You have to have a common earthing arrangement, so that when you look at this earthing arrangement, the standard use different terminologies. So that sometimes people mix up. So the selecting these earth wires, or sometimes everything we call as earth wire, but it is not like that. So there are correct terminology, and the selection of the conductors are also should be based on that terminology. Now I'll explain that. When you look at the electrical installation, we have electrical equipments, so that whatever the conductor which are, because we have a main earthing terminal, the conductor, the running from main earth terminal to these type of electrical equipments, so those are what we call as a circuit protective conductor. Now the M which I am denoting here is, all of them are electrical equipment, where they may have the exposed conductive parts, so where any person can touch. So here now we have to connect these exposed conductive parts to the main earth, and then we have to have a thing, so that depending on whether we are practicing TT system or TN system, So there can be different earthing arrangement, but everything we have to bring it to a common equipotential bonding bar, and that conductor we call as a circuit protective conductor. That is number one. And also you can see there are some non-electric equipment, so that we are, for example, it can be a metal door or it can be a metal pipe, those type of things. Also, we are in a certain abnormal situation or certain leakage, they can also they get certain voltage, and because of that we want to maintain their voltage level also at the same voltage. That's why we call as a equipotential, so that the same voltage. So to have that one, we have to connect them as well. So those connections, you can see the terminology what we are using is protective bonding. Okay, so that it's a bonding. This is protective conductor. Okay, so that there is a difference when you are referring this one, even IET wiring regulation. So there is a difference, selection method and everything. These are called as a bonding, and you need to have the connection from those equipment or those the metal parts to the our equipotential or the main earth terminal. So that those are we call as a protective bonding. And also there can be, you can have additional connection. Now you can see each and every electrical equipment, you need to have a circuit protective conductor. It's a mandatory requirement. Each and every these metal bodies and the whatever things where the people can touch. So even though they are not electrical equipment, you have to connect to the equipotential bonding bus, the main terminal. So that is also there. But you can have supplementary bonding. Those are we call as a supplementary bonding. So that in between those the connection where we can have supplementary bonding. So that is additional requirement. So that these are this 1 and 2 are compulsory. And if you want to have additional protection, you can go with the supplementary bonding. You can see that is also bonding, not a conductor. And then, so there is another conductor that we have to have from the main earth terminal to the either for your electrode, or you can have a separate cable up to the source earthing point, whatever way finally you do the earthing. So that we call as a earth again conductor. So that there are differences between them, because when you go to selection, so now 2 of them are conductors and the 2 of them are bonding. So there is a difference between those 2. Give me 1 second. Okay, and then when you look at the protective conductors, the selection criteria is given in the standard very clearly, so that if you want to select this protective conductor for any electrical installation, the first thing is you can see as per the regulation. So the first option what they are giving is a calculated method, so that you have to calculate what is your fault current. And based on that, you have to select your protective conductor. So that, but there is an alternative option also that is given as a second option, that is selected according to the regulation, the 543.1.4. So that when you look at these two, the one way is the selection can be done with it's called as a simplified method, where you are reluctant to do the fault calculation and then decide the exact value of the protective conductor size. You can go with this simplified method by looking at the phase conductor size. You can select the minimum size of the PE conductor or the protective earth conductor. So that what we are saying is, okay, if the phase conductor size is lesser than 16 millimeter, so then you have to go with the minimum PE conductor as a phase conductor size. And if it is in between 16 millimeter to the 25 millimeter, then your minimum size is 60. So that, for example, even with the 25 millimeter squared phase conductor, you have to use the 16 millimeter as your the PE conductor. And if you are going with the more than the 25 millimeter the squared cable, so then the 35 millimeter squared cable, then you have to go with the half size of the phase conductor. That is the simplified method. So this is the 16 millimeter is basically the 25 millimeter is taken for the copper conductor, and if it is aluminium, you have to go with the 25 millimeter squared cable. That is the simplified method. So that most of the times, even the consultant and many practitioners, so the without doing this earthfall calculation, because the manual calculation is very difficult. But now the advantage is there are a lot of software where you can the model your electrical distribution system, and you can easily calculate your short circuit current, earthfall current, everything can be done. You don't want to do manual calculation. So that if you are reluctant to do those calculations, then standard says us, okay, we can go with this simplified method. But the most preferred method is what they are telling as the first method is using the calculation where you have to use the adiabatic equation and then calculate the exact the size of the conductor, and you can use it depending on the pole current of the circuit. And also the standard says that, okay, you don't need separate conductor, but you can use even the building component or any other material as your the protective conductor. So that, for example, it can be a single core cable or even the whatever the any other conductor in a core or the cable. So that can also be used as a the protective conductor, or even the conductor in a common enclosure where we can use as the conductor, or we can use the fixed conductor or fixed insulated bar as the protective conductor, or even a metal covering. Sometimes we have a armor or sheath or screen, so that can also be used as the protective conductor. Likewise, there are many options available, but you can see that there is another requirement where if you the protective conductor cross section is less than 10 millimeters squared, if you are using any of these things, so then it should be copper. Otherwise, so if it is more than that, you can go for any other material. But if the conductor cross section is less than 10 millimeter, then it should be a copper conductor, copper material. So then that is the protective conductor. Then you have the protective bonding. That is different. Now the previously what I said was the conductor and the bonding. Bonding is where you have to have, depending on your phase conductor size, there is a minimum requirement. These are bonding. You can remember that the bonding is going for other type of metal, the structures and the metal, other type of metal equipments, not the electrical equipment. So that depending on the minimum cross section area of the main protective, the bonding conductor, you have to select the minimum size for the bonding conductor. Then you can remember there was a one called supplementary bonding. So that where you have the circuit protective conductor and the bonding, the equipotential bonding conductor bonding is the compulsory, but there can be a supplementary bonding as well. When you have, because these two are now you have this the earth terminal, so but you have to have a connection for those one, but there can be a situation where this one and that one are connected to a supplementary bond. It's an additional requirement, so that the way you can use the additional conductor, it's a supplementary, so that there can be supplementary bonding to enhance the connectivity. Because nowadays I'm coming to that one, we are talking about the three-dimensional earthing arrangement, or where earthing mesh kind of earthing arrangement where everything should be connected together, so that then only we can reduce this the voltage related disturbances as well as the electromagnetic interferences. So to achieve that one in the modern building, all these are basically recommended the nowadays. So where you have to have, of course, you have to have a protective conductor and the bonding, but as well as it's better to go with the supplementary bonding as well. So, and the third one is, okay, the fourth one is the earthing conductor, where you have the your earth terminal or the equipotential bonding bus, and then from there to your earthing system. There can be earth electrode, or sometimes you run a separate conductor up to the source, the earthing point, so that whatever way, but ultimately you have to earth it. So that that again, there is a separate requirement. So when you look at this, what it says is the minimum cross section area is the given, but you have to look at what type of the fault current can flow through these conductors, and depending on that, you have to size them properly. But the minimum cross section, these are minimum cross section. Don't take it as this is the what is needed, but it is not where you have to check whether what type of current is flowing through these conductors, and depending on that, you have to calculate the size. But even, for example, in a calculation, in a TT system, you get a calculation, and you find that, okay, you need something like a 0.75 millimeter squared your conductor. But keep in mind, you cannot put the points, okay, let's say 1 millimeter or 1.5 millimeter earth conductor, because the earth conductor should be minimum 2.5 if it is the protected against the corrosion by the sheath or the metal or the covering. Otherwise, it should be 16 millimeters squared. If you are using bare conductors, that should be the 16 millimeters squared, the copper, or the 16 millimeters squared, the coated steel. So that is the requirement. Now you can see you cannot reduce it less than 2.5, but you have to find out what is the actual current flowing through this conductor, and based on that, you have to size it. But if your size comes the less than 2.5, then you have to have the minimum 2.5 the earth conductor. Those are conductors. Conductor should be sized based on the calculation. That is the first option given by the standard. All the conductors, these earthing conductors and the protective conductors, should be calculated and selected accordingly. But there is a minimum requirement. Even though the calculation says it is lesser than this, okay, 2.5, you have to use the minimum 2.5 millimeters squared for the earth conductor. And other things I want to highlight is that the most of the location or most of the building, people try to find out the earth for the lightning arrestor, earth for the electrical system, earth for the telecommunication system, or sometimes we call them as a clean earth. You need to have a one earth for the clean earth, one earth for the dirty earth, something like that. Okay, are there anything like that? So the keep in mind, okay, if you define it like that, you can define different type of earth. So that now the modern standard, none of modern standards and the regulations are accepting that. What they are telling is you have to have a equipotential bonding. In a same place, you cannot have different type of earthing, because if you are maintaining different earthing, that can create many problems. So especially in terms of the electromagnetic compatibility, that is anyway not accepted. So that because of that, keep in mind in a modern building, so there's something called clean earth, dirty earth, electronic earth, instrumentation earth. Likewise, there is nothing called like that. Now the modern standard, they do not define those type of things. What they are telling is you have to have a equipotential bonding. So then as per even for the IEC and all the other standard, what they are telling is, okay, now don't go for different type of earthing or earth electrode for a particular electrical installation, so that this single so individual earthings are not recommended nowadays. And also the common thing is also not recommended like that that can also create electromagnetic interferences and the electromagnetic issues. So that the modern thing is what we call as a equipotential bonding, where it's a three-dimensional type of bonding where everything within the building is connected together. You don't want to worry about that because we are providing a low impedance part too. If we have any abnormal current, it can be even a harmonic, even any other things that will find out a low impedance part and will go back to the whatever the origin point through the low impedance part. So that our requirement is to provide a low impedance part. So that's why even in the TT arrangement, so there is that is not recommended nowadays for the modern, when we are working with modern equipment, because that will not give a low impedance the return path. So that we want to provide a low impedance return path, then only, because the most of the time damages are not happening because of the current, damages are happening different voltages. So if you have different voltages, then that can create the lot of interferences, a lot of issues in the modern building, especially when we are working with the power electronic devices and the modern sensitive equipment. So now the current practice is where we have to have a three-dimensional earthing network, so that like that, okay, even a high riser or whatever installation, even your rebar and the structural system we can use, because we have enough the bonding conductors there. So that, for example, when you look at the rebars in the building, so we have enough rebar so that that can be connected together, creating a equipotential bonding. You don't need to have separate, or you don't want to spend additional earthing system, because there are natural components. So that because of that, if you plan it from the beginning, so that without any additional cost, so you can easily implement this three-dimensional earthing arrangement in any building environment, because we have enough the natural component where we can use as our earthing system. So that when we have a structure, even for different floors, obviously there are a lot of the rebars and other connections where we can use them as our structural earthing. Now you can see in here, when we before casting the concrete, you can easily put the certain type of earthing connection inside the rebar arrangement, and then that will work as a earthing network. So that here also you can see this is the modern practices where easily you can come up with a very good earthing system and the equipotential bonding within the installation, so that you can minimize many the problems that can arise during the operation if you design it from the beginning. So that because if you try to adapt this one at the later stage, then you will face a problem. But during the design stage, you have to discuss with the civil engineers and the other the related areas, and then they come up with the equipotential bonding structure. So this is the current practice, and this is the standard way, even for the lightning protection, even for the safety, everything. Now the standards, all the standards, they are talking about this type of a equipotential bonding. And also, when you look at this 18th version compared to the previous version, there are a lot of changes happen. I am just highlighting few changes, few such changes which you have to the look at. You can see there are a lot of things. Some of them are extensions, some of them are complete changes happen, and also new additions were done to the 18th version by considering the modern requirement. So I will just highlight few things. The most important thing is, now traditionally we know that when you look at a distribution board, we are talking about the main components are your the circuit breakers and the 4 relay. Those are the main equipment. But now the people understood that those are needed, but there are some other requirements as well. Now, for example, in electrical installation, there are different type of faults can happen. So that there can be live to live, live to neutral, those type of things. We are even with our existing protected device, they can detect that one. So now these are even live to earth, those type of things we can detect by existing equipment. But the problem is when you go to something like the arcing, because you may aware that okay, in the recent past there were a lot of buildings were collapsed, and also they got fire due to the arcing. And due to that one, especially when you go with the high rises and the condominiums and many other apartment buildings, those type of things, there is a very high risk where if there is an arcing can propagate, and that can lead to the fire hazard. And because of that, now in this standard, they are specifying that we have to go for the arc fault detective devices, so that other than the circuit breakers or the overcurrent devices and the fault devices, now there is an additional recommendation, that is arc fault detection equipment, because to reduce the risk of the fire due to this electric arcing. So now there are equipment like that. Now what it says is, so the locations like the sleeping accommodations, of course, like condominiums, apartment buildings, those type of, even hospitals, those type of location, of course we have to go with these type of things, because there is a very high risk of the arc faults, and they can there can be a fire risk due to that one. And because of that, we have to design our electrical distribution system adapting this arc fault for those type of location. Likewise, okay, if there is any probability or the possibility of arcing in a particular installation, so that it's up to the designer to look at and identify that whether there is a risk. But the standard says that these type of locations, like sleeping accommodations, and where there is a location with the high fire risk, and the location with the combustible structures, and where there can be a fire propagation structures. So if you have that type of things, okay, no matter what type of building, you have to now incorporate this arc fault detection as an additional. These are new additions that was not in the previous versions. And also now when you look at this the new the regulation, there is another new addition. So that is this voltage disturbances and the electromagnetic disturbances. That was there even in the previous one, but now it is more highlighted, and these chapters were expanded, adding more and more details, and how we have to adapt this voltage disturbances and the electromagnetic disturbances, because now we are using more and more very sensitive equipment and more power electronic equipments which are working with very high frequencies, and also they can generate a lot of electromagnetic radiation, and also they can disturb by the environmental electromagnetic radiation, so that when we are designing our electrical system, we cannot follow earlier traditional type of the distribution system, assuming that only we are getting 50 hertz the power frequency, the waveform. Now our system is more distorted, and we are getting a lot of high frequency component, so that we have to take those things into the account when we are designing. I will quickly go through them because we have limited time. And when you look at the first one is the over voltage protection, or what we call as a transient over voltage protection. As I said earlier, we were discussing even when you look at the distribution board, main equipments were the overcurrent protective device and the earth fault protective device. But now with the regulation, these changes, they are specifying not only those two, but we have to have arc fault detection as well as transient over voltage protection as well. So because earlier even if there is a minor voltage disturbances or voltage over voltage, so our equipment were able to manage that, because they were robust and their insulations were very high. But now when you look at nowadays equipment, they are not like that. Because for example, even if you take a classic example, earlier we were using incandescent lamp, but all of them were replaced nowadays by the electronic, the LED, electronic based LED, where even a minor lightning surge can even damage our lights. So that because of that, this the transient overvoltage protection nowadays has become also a mandatory requirement. So that whatever if you have a service coming from outside, then those services should be protected with the surge protective devices, so that there is a new the additions in the regulation. So as per the regulation, now these are new additions. So what they are telling is, okay, in the mark, okay, normally when you look at this SPD, there are type 1 SPD, type 2 and type 3 SPDs. So that if a surge comes, so that what they are telling is you have to have a certain type of arrangement. So the most of the times the majority of the surges will absorb by the first equipment, but there will be certain part can travel to the other side. So that generally we are taking that like 90% of the surge can absorb by the first surge protected devices if you have a type 1, but there will be a 10% can go to the other side. So then the second surge protective device will absorb the 90% of the incoming surge, so that 9% will absorb by the second surge protective device, but there can be something like a 1% can go to the other side. So if you use a third surge protective devices, you will see the 0.9% will absorb by that surge protective device, and there will be only 0.1%. Now, earlier if we consider that it is 100%, now that if we use 3 cascaded surge protective devices, so that will reduce to something like a 0.1% the total energy. So that is the main idea. So that we have to have a cascaded surge protective devices, so that we have to look at where that surge can occur, and from there onwards, so that we have to have a cascaded surge protective devices. They will manage our transient over voltages. As I said, when you look at this part, I'm putting a little bit more time on this part, because even for the SPD selection, the selection criteria, risk assessment, everything is newly added to this 18th version, so that there are different the type of SPD connection. Those are called as a 4+0 and the 3+1, and depending on the whether you have a TT earthing arrangement or TN earthing arrangement, so there are different recommendations given in the standard. So as an example, I'm not going to give all those details, but just to give you some the few examples, when you look at the TN earthing arrangement, you can either go with the 3+1 or 4+0. But when you look at the TT arrangement, so the TT arrangement, this 4+0 is not recommended, because the problem is, for example, when you have a certain type of the internal leakage in the surge protected device, so that the current can pass through like that through your high impedance earthing, so that will go to the source. But you can see this flow current IF is very low in the TT arrangement, because obviously we know that the earth flow currents are very low in the TT arrangement, so that even though you are putting a overcurrent protective device there in the surge protective devices, that will not detect this earth faults, because obviously overcurrent protective device will not detect earth fault, and that's why this the 4+0 arrangement is not recommended. If you want to put the 4+0 SPD, you will see that you have to put your RCD in the upstream, not the downstream. So now here you can see your RCD is in the downstream, but you cannot put the RCD in the downstream if you are going with the 4+0. Likewise, there are the many recommendations given. I advise you to go through this chapter and get some idea, because nowadays if you are not just putting SPD is not enough. You have to coordinate them and put it in a correct manner. Otherwise, you will not be able to manage your very sensitive electronic equipment in the future, so that they can damage very easily. Even when you have a surges or the lightnings, the lightning can damage them very easily. And the other thing is, okay, nowadays, as I said, not only we are working with power frequency, now we are working with many high frequency component as well. In our system, most of our systems are now distorted because of the harmonic, because of the other type of interferences, high frequency, the switching, those type of things. And because of that, the standard added new requirement: when you are running these cables, you need to maintain minimum separation. So that, for example, if you have the power cable and the signaling cable, you cannot run them in a separate conduit, or you cannot run them in the same ducting. You have to have a separate, the separation, minimum separation, depending on, for example, if you have a 400 the volts, the supply, then there is a minimum requirements where you have to have a certain minimum separation. And also, when you look at the modern, the standard, they are also recommending, okay, normally if we are putting our cables in PVC conduits or the plastic or those type of non-metallic conduits, they will not support to your electromagnetic interferences, because they are just plastic, no shielding. But the new standard, what they are telling is better to go with the metal, the cable ducting and the cable waste, so that will help you to reduce the electromagnetic interferences. At least, okay, you can go with the certain sheath or the armor, okay, the steel wire armor, not the aluminium. Then you can reduce this type of interferences, and even the selecting the your cable ways and the ducting, those type of things, there are certain recommendations. Now, as shown here, you can see that rather than going with the flat, the metal trays, so the better to go always with the certain type of this type of the deeper U-shaped ones, so that we will get a lesser interferences. So that because that is anyway covered by 3 direction, but rather than exposing our cable to the outside environment, if you can go with the deeper this type of tray, then we can reduce the electromagnetic interferences. And when you look at in terms of the different options, the best option is considered as if you can put these type of sensitive equipment or the cables inside this round the metal conduits. So, and you have to earth them properly, then you can minimize the most of the interferences. The next option is you can go with this type of the trunking system, but metal with the covering. The third option is, okay, at least you can go with this type of narrow duct, so that then again you can reduce the interferences. And also sometimes you may have seen that many installations you are using this type of sometimes the mesh kind of the cableways or some kind of a slotted this type of the ducting or the trays. So when you look at that trays, this slot arrangement is also important, so that either you can put these slots perpendicular to the cable way, or for example like this, so that way is not recommended, because if you have if the cable is running like that, and if you have a slot like that where the electromagnetic radiation can propagate outside the cable tray very easily, and also the outside interferences can easily come in and interfere with your cable. So that because of that, the best way is if you can have the fully covered cable, but there will be a problem with the heat dissipation, so that you have to have a certain compromise, so that when you are selecting time, okay, rather than going with this type of arrangement, better to go with the either slotted, but the slot you have to make sure that slots are perpendicular to the cable way. Sorry, not the perpendicular like that. Okay, if the cables are running then, so it should be parallel to the cable, the path, but not the perpendicular distance. And also you have to have this aggregation. As I said, the standard says that if you have different systems, you have to have a different type of the cable trays, so that especially when you have the sensitive cables or the cables which are carrying sensitive signal like analog signals, digital signals, you need to fully cover them with the metal, the ducting. And the other cables, okay, you can have a separate the ducting systems or cable trays. So where for example, power cables will be here, and the analog any auxiliary circuits will be separate like that. Okay, you can have a separation rather than putting them in the same runaway. So that those are some of the practices we have to have in the modern building. And the other thing is, in terms of the electromagnetic compatibility, what the standard says is you have to have just having shielding or metal conduit is not enough. You have to earth them properly. So without earthing, okay, that the effect is not there. So that especially when you are working with high currents, so then because the high currents can create inductive coupling. Normally there are two types of coupling arrangement. One we call as the capacitive coupling. Other one we call as inductive coupling. Inductive means the magnetic coupling. Capacitive means the voltage coupling. The voltage coupling means if you are working with high voltages, there can be a certain coupling from one circuit to the other circuit. Those are we call as a capacitive coupling. Inductive means if you have higher currents, then there is a possibility of inductive coupling. So you have to keep in mind that when we are putting shielding or this type of metal conduit, in order to reduce the inductive coupling, you have to earth both sides. The single side is the earthing is not enough for the inductive coupling. So the capacitive coupling, it's enough to have single side earthing, but for the inductive coupling, you need to have both side earthing. So that and also there are certain additional requirements. I'll just go to it because the time is already passed, and few other the main concerns are there, especially now you are aware that in Sri Lanka we cannot use other than the type G socket outlets. So that normally we call them as a 13 ampere socket outlet, but the only possibility is you have to wire them using as per the BS7671. So that only possibility is you cannot use any other type of socket outlet. Only type G is allowed from 2019 January 1st onwards in Sri Lanka. You cannot even use the appliances cannot be sold in here without type G, the plug tops. And when you look at these type G, these circuits, we can wire them either using ring circuit or radial circuit. Sometimes people interpret as, okay, if it is 13 ampere, you have to go with the ring circuit only. But it is not like that. You can go with the ring circuit or radial circuit, depending on the requirement. Either you can wire them using a 13 ampere ring circuit, or you can wire them using a 13 ampere the radial circuit, or you can wire them using a 20 ampere radial circuit. It is 20 ampere, then your protected device is 20 ampere, then it should be a radial circuit. So that these are also given, these diagrams and everything is given in the standard so that we can easily follow. Now this is you can see it's a ring circuit. Even you can have a spur lines where you can extend. For example, if you want to have an additional socket outlet, you can have only one additional socket outlet, so that where you can tap out from one socket outlet and we can go with the one additional, or you can go with the one additional twin socket outlet. If you want to extend more than that, then you have to put the overcurrent protective device or the circuit protection, and with the circuit protection, you can extend to a additional socket outlet. So this is the ring circuit, and similarly, so you can have the 13 ampere the radial circuit. So if you have a 13 ampere radial circuit, that should be wired with 4 millimeter squared, and if it is 20 ampere radial circuit, that should be wired with the 2.5 millimeter squared. And also in the new standard, so they have highlighted that this energy efficiency in electrical installation is the very important. And also because of that, they have specified that the maximum voltage drop allowed for the designing part, where you designing and the operation, so that depending on the type of the circuit, so the allowable maximum voltage drop is also specified, so that when you look at the appendix 16 of the energy efficiency, this is the new addition to the standard, so that there are certain requirements where you have to make sure that that will not exceed the voltage levels given in this table. Okay, so finally what I want to highlight is, okay, now all of you are traditionally know that when you look at a distribution board, the traditional protective equipments are your overcurrent protective devices and the earth fault protective devices. But now, as per the new requirement, there are additional requirements where not only these overcurrent protective devices and the earth fault protective devices, but you need to have a arc fault detection as well as the surge protection or the transient over voltage protective equipments as well, because now we are working with more and more electronic based equipment, more and more very sensitive equipment. So because of that, we need to have an additional protection. And especially when you look at the arc faults, because the people experiences many the fire hazard, especially in the modern building, because the modern building there can be even a minor the arc fault can even propagate and create certain type of the fire hazard. And because of that, this arc fault, the detection is also very important nowadays, especially like apartment buildings, the hospitals and schools, those type of locations where if there are higher risks, then you have to have a arc fault detection on those type of locations. Similarly, even for the over voltage protection, now earlier, so because since the surge over voltage protections equipments are expensive, people were very reluctant to put them. But now, as per the standard, so that you cannot deviate, you can deviate only if you do the risk assessment and show that, okay, there is no transient over voltage risk. Otherwise, if you are not putting risk analysis, then it's mandatory to put the surge protector. Coordinated surge over voltage protection is mandatory, but there are certain the location, these are mandatory. Even you do the risk analysis or not, the standard says that, okay, some location it's mandatory to put this surge over voltage, especially the locations where the people are working and the people are accommodated. So those type of locations where if there are higher risk or if there are any public services, then these surge protective devices are mandatory. So that's all what I want to tell you. So I have taken a little more time, something like the 10 minutes more than what I have expected. So that's all I want to tell you. And I hope, Minaj, we can spend little more time for the questioning and answering. So if you have any the doubt or questions, or if you want to share some knowledge, your knowledge, so that you can put those questions to the chat box with the available time. So I'll try to answer as much as possible, or else you can raise your hand so that the host will allow or host will unmute you so that you can ask questions. So that I think we can allow certain questions. There is a Tusita Pereira is raising. Is it possible to unmute them? I don't know whether it is possible to unmute. We'll look at the chat box and see whether there are any questions in the chat box.
Yeah, so small question. Just a quick question. How to size the earth conductor from, let's say, if it's a HT transformer building which has HT transformer, how to size the from the transformer neutral to earth, that conductor, and the from the transformer frame to earth, how to size those two earth conductors?
Yeah, it's a very good question, and most of the times people ask that question. Okay, how to size? Because sometimes people get confused about that. As I said, when you look at the conductors, so the conductor, there are circuit protective conductor, or from your earth, the equipotential bonding bars to the transformer, there should be a conductor. So if you say the conductor, then that should be sized as per the adiabatic equation. So that you have to calculate the fault current even from the transformer body, because it's again a earthing conductor. So that should be sized based on your fault current. You have to do a fault analysis and check whether even for the transformer, so the transformer, there can be either ST fault or LT fault. So you have to check whether which one creates the higher fault current. For example, when you look at the draw it here. Now, for example, let's say if you have a substation where your high voltage and the low voltage side is there, so that here you have the neutral point. Okay. Now, when you look at the transformer body, there are different options available. So that depending on the requirement, either you can have the separator. Normally, you will see that in the distribution transformers, what the CB and the LECO is following is they are maintaining two different earths with the electrically separated two different earths, so that even if there is a certain fault happen in the high voltage side, that will not transfer to the low voltage side. So when the other possibility is where you can connect them together, so that in that case, depending on your electrode resistance, there will be a voltage, so that can transfer to the low voltage side. But in both cases, what you have to do is you have to calculate this high voltage current as well as the low voltage current, IF2 and IF1, and check whether what is the fault current. And based on that fault current, you can size these conductors. And similarly, as you said, if you have your electrical equipment, now you have, let's say, L1, L2, L3, and the neutral, and also you will have a P conductor. So the P conductor, then again, as I said in the presentation slide, so that should be sized based on those calculations, or you can use that simplified version. Whatever way you have to do the calculation. Now, both of them are conductors. Which are done for the bonding. Bonding, there is a separate table to select the bonding conductor. But the circuit protective conductor and the earthing conductor, depending on the current you are handling, you have to size them and select them accordingly. Is it clear?
Yes, sir, yes.
Okay. Any other question?
Doctor, there are some question in chat box. I think you can.
Yeah. Can someone read it? Let's see. First one is the email, the lecture slides. Of course, I can share the lecture notes. No problem.
First one is, can we use 1.5 square millimeter cable with 10 ampere MCB for 13 ampere socket?
No, as per the standard, because when you look at these main distributions, so that you have to have a 20 ampere and the 30 ampere. But if you have a spur lines, so where you can use the 1.5 millimeter square, there is no harm of using, but you are restricted, because now when you look at the IET wiring regulation, earlier you had certain type of diversity factors were defined to look at, okay, what is your calculation. So that because when you look at this 13 ampere socket outlet, if you are using only one 13 ampere socket outlet, making sure that So this 1.5 millimeters squared is sufficient for the maximum demand. Because if you have number of shock outlets, so the problem is now this is 13 ampere and this is 13 ampere, let's say like that. And if you are wiring them, using the overcurrent protected device, now you can see if you add them, the maximum demand will be, in that case, the 26 ampere. So that then probably 1.5 millimeters squared with the derating factors will not be sufficient. But for example, if you have one the socket outlet, because other thing is the standard also says that when you are selecting cable should be selected, cable and the protected devices should be selected for the maximum demand. So that otherwise you will violate that requirement also. So that look at, if it is a one socket outlet, if your maximum demand is 13 ampere, of course you can wire using 1.5 millimeters squared with the 10 ampere circuit breaker, but the 10 ampere will not be sufficient because then it reduces the maximum demand. That's why this the standard says that okay, you have to, if you are wiring then the 20 ampere with the 4.5 millimeters squared is given as a standard requirement. I hope I have answered the question. Okay,
there's another question from Gayani Jayaman. If there is structural earthing system, is it required to have separate earth pits and test points?
Yeah, normally, okay, these concept like the test point and the separate earths came with the practicing of this the TT system. So that if you're going with the TT system, because in the TT system, your earth electrode resistance is a matter. So that because the standard tells us, okay, what type of earth electrode resistance are needed for a TT system, and you have to maintain for example, in a electrical requirement, so your earth electrode resistance should be less than 200 ohms. For a 30 milliampere, the RCD protection. Likewise, that is mentioned only for the TT arrangement. In the TN arrangement, because your earthing is anyway there, so that because even for the TT arrangement, that piece came because of the earth loop impedance, so that can create a higher potential rise in the earthing system. So, but that problem is not there for a TN system. TN system, we are not talking about what should be our earth electrode resistance value. Nothing is needed because anyway, your electrical earthing system is connected to the source earthing system. So that if there is a earth fault, so there is a low impedance path. That impedance path will not rise the earthing system voltage. So that because of that, you have a higher protection, higher safety in a TN system than the TT system. So this earth electrode resistance matters. So even when you look at carefully read the standard, you will understand that. So this earth electrode resistance, the values are specified for a TT system, not the TN system. TN system, you don't care. So what is your earth electrode resistance matter, because your earth fault current will not go to earth electrode, because there is a conductive path, the earth fault current. So what we call as a IG, that is the ground current will not be there in the TN system, so that you don't want to worry about your earth electrode resistance in a TN system. But keep in mind, so when there is when your earth electrode system is connected to a lightning arrestor system or your external lightning protection system, so then because when there is a discharge, that discharge current can go to ground and the ground potential rise can increase. So that because of that, so you have to minimize this the resistance of the earthing system. In that case, sometimes okay, in order to just to measure what is your earth electrode, the total electrode system, even with the structural earthing, so you can put the few the inspection points where you can connect the earthing measurement equipment and measure it. Now, for example, let's say if you have a building, I'm drawing the top view, so that you have down conductors and the different locations, so that the where, in order to measure the earth electrode resistance and check whether that is the below 10 norms, you can have certain inspection point to measure, so that you can put 3-point earth electrode resistance meter, and you can measure them in a different direction. What is your earth electrode resistance value for that one? But in terms of the safety requirement, you are not caring about earth electrode resistance for a TN system, because you have a low impedance path. So then you don't want to worry about that.
Doctor, we will give another one chance for hand-raised person. And there are so many questions, then I will ask them to, they can send an email to your email ID later if they have more questions. Okay.
If you can share them, these questions, because probably that will be recorded, so that even I will try to answer them, and with their email addresses, if you have collected their email addresses, I can reply them.
Yes, we will do that, and we will give one chance for that one hand-raised person.
Thank you, sir. The question is regarding the residual current protection in data centers. So I have met clients with no likelihood for having any residual protection for their racks, data racks, because they don't need any tripping. So to maintain 100% uptime, they need to avoid residual current protection. So I just need to know whether BS allows for such cases to have like residual go without residual current protection.
The BS allows in those type of locations, those are considered as a special installations, or where you can go with the isolation transformer. And if you have an isolation transformer with the SCLV system, where your secondary side will work as a totally separated, where even if you touch a live conductor, you will not get any electric shock. But only thing is, you can put certain type of insulation monitoring devices. So where if there is any insulation failure, because this residual current means if you have a certain leakage, that will be detected. So that can be done even by the insulation monitoring devices. The only thing is, insulation monitoring device will give you an alarm if there is a drop in the insulation. So that where you can act on that, and without disconnecting the system, you can work with that type of system. So we are that special kind of installations where you can go with that type of protection as well, where rather than having earthfall protection, you can have the separated. Some of them are functional requirement. Okay, if you have a functional requirement, then anyway you have to run the earth conductor, but that will work as a separate the system with the IT.
Thank you, sir. Without isolation transformer, can we go like that? It's just with the isolation transformers only.
Because insulation monitoring is also considered as a way of the residual current, the monitoring. So that, but the only thing is there should be automatic disconnection. So if you have because what will do by the insulation monitoring devices is continuously monitor your insulation level, and it detects whether there is a drop in the insulation level. So if there is a drop, that will give an alarm, so that you can react first. But if the insulation level drops the continuously, because that can create a harm if somebody is there, and if somebody touches your system, so then that can create a hazard situation. If it is the fully isolated, or even for example, if you have certain type of the insulations in your the flow levels like that, then with that minimum risk, you can go ahead with the certain isolation type of but it should be a separate installation or separate system.
Okay, thank you, sir.
Any other questions, Minoj?
There are many questions, Doctor. What I will do, I will send you the questions later. That answers we will publish in our website. Thank you very much, Doctor. Spending your valuable time. I know you are a very busy person. So thanks for sharing your knowledge and to trying to enhance that market professional society experience to deliver quality projects with good experience. So I think this is a very big subject. We will after couple of months, we will try to arrange if possible part 2. Yeah. So thank you very much, Doctor. Again, all attendees, we will publish questions and answers. You can go to our website after next week or after a couple of weeks. You can go to, there's a tab called Knowledge Hub. We will share that question and all answers from Dr. Asanka. Okay, good night. Thank you all and Dr. Asanka.
Yeah, thank you very much, and thanks for the listening for all the participants. I think we got a very good number of participants. So that thank you very much for the.
Actually, Doctor, this our participants are 100 past participants that limited. We will update because we did not assure this much participants. In our next session, we will update it to next level is 500. We will update to that level.
Right.
Okay.
Okay. We will.
Okay.
Thank you very much, and good night to everybody. Thank you.